This next section is going to review thermochemistry, but it was kind of a big chapter, so we're going to split it into two different videos. So this first video is going to start with a review of some vocabulary. Temperature, we said in the last chapter, is the average kinetic energy of the particles. And another way to say that is that it is the speed of the particles. And you do need to know that the units for this are going to be in Celsius or Kelvin. But in this chapter, we're going to focus on Celsius. The next word you need to know is heat, and this is tough because I know a lot of students have trouble with differentiating between heat and temperature. So heat, you can consider this as a flow of energy, and the unit for this is going to be joules or kilojoules. So watch out for the unit, and that can help you distinguish whether it's going to be heat or temperature. Our next word is exothermic, and we're going to compare this to endothermic reactions. For exothermic reactions, these are going to lose energy compared to endothermic reactions, which gain energy. For exothermic, you're going to have a negative Q value. Remember, the negative does not mean less than 0, it just means that the heat is leaving the system. And for endothermic, it's going to be positive. And again, that just means that heat is going in. You also need to know that for exothermic reaction, these are going to feel hot to the touch. So the test tube would feel hot, or the beaker that you're doing the experiment in would feel hot. Whereas endothermic is going to feel cold. And then for exothermic, these are the ones that are favored in nature because they usually have a lower activation energy. And we're going to draw the activation energy now. So for exothermic reactions, we're going to draw these energy diagrams for both of them. For exothermic reactions, they tend to have energy that's going to be lower as a product. So it's going to look like this, versus endothermic is going to gain energy, so the final energy will be more. So first of all, this is potential energy on the y-axis. And there are several things you need to be able to label about this. The energy of the reactants is going to be this first line here. And the energy of the products is going to be on the right. Activation energy starts at the reactants and goes to the top of the hill. So don't go all the way down to the x-axis. It's from the reactants to the top of the hill. And that is called activation energy. And we're going to define that in just a minute. So notice the activation energy is higher for endothermic reactions, which is why nature favors the exothermic reactions. And the last major thing you need to know about this is the difference between where you started and where you stopped, and that is called enthalpy. That's the heat of the reaction. It's the difference between the reactants and the products. And one other thing is you should be familiar with how a catalyst affects this. So if you add a catalyst, it lowers the activation energy. So let's write down a few of these words. We talked about activation energy. This is the energy required to start a reaction. So it's not the total energy at the top of the hill, but it's the energy from the reactants to the top. The next word is catalyst. You need to know two things about this. You need to know that a catalyst will speed up a reaction, but you also need to know how it does that. And it does it by lowering the activation energy. So that the particles don't require as much energy to get over the hill, so they can turn into products faster. All right, our next graph is called a heating curve. Although it doesn't really look like a curve. It looks more like a staircase. And this is showing you how the temperature changes as you change states of matter. So first of all, let's just review. You start with a solid. And at a certain point, you're going to get to the point where a solid starts to turn into a liquid. So at this point, you're still putting heat into the substance, but notice that the temperature levels off because during a phase change, the heat is used to change the intermolecular forces or the bonds. It's not used to speed up the particles. And so when the particles don't speed up, then the temperature doesn't change. But once you get to the end of that flat line, then you can change the temperature again. So now we have a liquid. Another flat line means another phase change. And then we have gas at the top. And there are some equations that we used for these calculations. You are going to use the MCAT equation anytime you have a diagonal line. So you can use it for the gas line, the liquid line, and the solid line. And you're going to get C from the reference packet. And then delta T means the change in temperature, so it would be final minus initial. For this first flat line, you're going to use Q equals the mass times the delta H fusion. And for the top flat line, it's the same equation except you're going to use delta H vaporization. Both of those H's are given to you in the reference packet as well, so you just have to know where to look for them to look them up. Make a note, it's really important that you can explain that there is no temperature change during a phase change. No temperature change during a phase change. And you also should be familiar with the word specific heat. So let's go ahead and define that. Specific heat, this is the letter C in the MCAT equation. This is the energy required for 1 gram of a substance to increase by 1 degree Celsius. So it's basically a measure of how well something absorbs heat. Something with a high specific heat takes a lot of energy to make it change temperatures, and something with a low specific heat would be like a metal that changes temperature really easily as you apply heat to it. And we have just a few more vocab words for this video. The next one is enthalpy, which is the heat of the reaction. In other words, it's the difference in energy between the reactants and the products. And for this one, exothermic was favored. And the symbol that we use for this is delta H. We also have entropy. Entropy is another word for disorder or chaos, randomness. All of those words kind of mean the same thing. And for this one, we say that nature prefers more disorder. And the symbol that we use for this is delta S. There are several ways that you can increase, or I should just say change the disorder. So these are ways to change the disorder. You can change the state of matter. So solids have the most order and gases have the most disorder. You can change the temperature. So things that are hotter are moving faster, so they have more chaos or more entropy. And you can change the moles. And by moles, I mean the coefficients in the balanced reaction. So if we had a reaction like this, we're looking at these coefficients. So on the left side, we have a total of 5. On the right side, there's nothing there, so it's just a 1. So we say we went from 5 particles to 1 particle, and so the chaos has decreased, because the more particles you have, the more entropy you have. And the last thing for this lesson is whether or not a reaction is spontaneous. So a spontaneous reaction means it occurs by itself. And this is going to happen, it will always happen when you have both conditions that are favored by nature. So if it's exothermic and it creates more disorder, the reaction will always be spontaneous. spontaneous. If neither one of these happen, then it will never be spontaneous, and if one of them does but the other doesn't, it's dependent on temperature. But all you need to know is the conditions that create a spontaneous reaction. And we will continue with thermochemistry in the next video.